Okay, Mike's here, we can get started now. All right, just a reminder, the Learn Smart for Chapter 12 is up and live, and we'll finish next week, Monday. And since this is the second to the last class, and you only have one more quiz left, and I didn't bring anything in, I'm not announcing that we'll have a quiz on Friday. And it's dead week, I know, but since the quizzes don't really take away anything from your grade, they can only help you. I don't feel too bad about it. And they will help you study. Also on Monday evening at 5:30 in here, I think there should be no exams at that time. We're going to have a review session. And the exam is Thursday at 10:30. Okay? Any questions on that? One thing you should make sure you do is if you check to make sure all of your Learn Smart and Connect points show up in Blackboard, because if they're not, I know some seem to be missing, and I'm not sure if it's because you didn't do it or somehow they didn't get transferred. So if you think you have points that should be in Blackboard and are not from the Connect, let me know and I'll try to track that down, because I do need to make sure that's all taken care of before final grades do get entered in a couple of weeks. So, okay, I want to continue talking about electrophilic aromatic substitution. If you recall from last time, we talked about this reaction where we can take a benzene ring and react it with an electrophile, but not in the usual sense like we think about for double bond chemistry. What we need, because of the very high stability of aromatic rings, we need electrophiles which are much more reactive than just typical electrophiles. So in this case, bromine, Br2 just by itself, although is a quite reactive electrophile towards most double bonds, is not reactive enough to react with a benzene ring. So we have to activate it. We have to make it even more electrophilic, more electron deficient, and we do that by using Lewis acid catalysts to bind to that. That withdraws electron density towards that Lewis acid, weakening that bond, making this more positive. Okay? And that's true for all the chemistry we talk about for electrophilic aromatic substitution. We need to have very reactive electrophiles to get any reaction to happen. And then the other difference is, although the first step is the same as reaction of any double bond, you add an electrophile to the alkene, the pi bond, to break it. You form a carbocation. You don't add a second group. Okay? What happens is, and we can draw this plus charge in a benzene ring in resonance, so it actually exists on 3 different carbons, that plus charge character. It's spread out through the ring. But to gain the stability back for the aromatic ring, instead of adding a Br minus, you take the proton off, and so those electrons can flow back into the ring to make that aromatic system. So overall, we've substituted a hydrogen for a bromine. Okay? So this pathway that would form just addition to a double bond is not the favored path because it's a higher energy path. Reforming that aromatic ring is what's preferred. So we saw last time that besides Br2, we can add all kinds of electrophiles. Right? We can add groups like NO2. So here are conditions for doing nitration, or sulfonation, where we can end up with either an NO2 group, nitrobenzene, or benzene sulfonic acid, an SO3H group. Okay, the mechanism is exactly the same. The only difference is we have to somehow generate these very reactive electrophiles in order to do that chemistry. So certain conditions, and if you remember the reagents, you know you put on an NO2 group. If you just mix together nitric and sulfuric acid, concentrated acids, that generates NO2 plus as a very reactive electrophile. So just like I showed with Br plus on the previous slide, NO2 plus will react. Okay, and I want to reiterate again the Lewis structure for a nitro group. We're going to talk about this in more detail today. So if you look at this, it's N double bond O, single bond O, sorry I'm running out of room there, with a minus on the oxygen and a plus formal charge on the nitrogen. And in any resonance form you draw with that nitro group, it is that nitrogen will always have a plus charge. So it's something to realize that groups that have nitro is a very strong electron withdrawing group. Okay. This sulfonic acid, also we can draw the benzene sulfonic acid. We can draw it like this, okay, with all the bonds shown out there. That's SO3H. And keep in mind that the polarity of these SO double bonds is towards the oxygen. So again, this sulfur has a lot of positive charge character to it, which means this group is also an electron withdrawing group. Okay, I highlight that now because we're going to come back and really talk about how those kinds of groups influence further chemistry. We can add halogens, and I'll just briefly remind you, last time we talked about Br2, Cl2, and I2. All those halogens we can add, again, some way to activate to make the active electrophile. But we can pretty much add the halogen that we want. Okay? Questions on all that? That's pretty much all that we talked about last time. I want to continue talking about further electrophiles that are very important, and that is carbon electrophiles. So we talked about this reaction, the Friedel-Crafts alkylation. Reaction which is over 100 years old, which is still used today, and very significant for forming carbon-carbon bonds to substitute benzene with other carbon groups. Okay, so R could be many different things. Again, in order to do the chemistry, you have to have a very reactive electrophile, and that electrophile has to be on carbon. And so the thing we want or need is carbon with a lot of positive charge on it. It could be a free carbocation. Those are very reactive free carbocations. Or it could be if a carbocation can't be stabilized, like in this case, if you use a methyl chloride, okay, pulling the chlorine off to make a methyl carbocation, that's a really high energy carbocation. But a Lewis acid can still activate it. So in this case, in the presence of aluminum trichloride, what happens is you, again, weaken this bond, polarize it by forming a bond with the chlorine. In this case now, the lone pairs of the chlorine are reacting with the empty orbital on the aluminum. Okay? That makes this now very strongly positive. This group is now polarized negative. For methyl, that's enough. You can make it a pretty positively charged methyl group, enough that it will react with the benzene ring. I'll be honest, this doesn't work at room temperature. Okay? We do have to heat this up, and probably over 100 degrees to get methyl to work. And that has to do with the ease of forming carbocations. So the mechanism is exactly the same. You have some alkyl group. Here it's just generically written as R, attached to a halogen. The Lewis acid pulls that off, and so if you will, I'll write it as an R+. Okay? Because in some cases you can form free carbocations. So the electrons react to form our intermediate. And I highlight that hydrogen again to remind you that the carbon, the electrophile added to is sp3 once you do that. And that's the hydrogen that has to come off then to make the aromatic product. So again, this hydrogen, okay, if we have this as the byproduct, okay, this hydrogen will come off to form HCl and form the product. Now again, keep in mind that plus charge that I originally generated, I didn't draw all the resonance forms, but you should know that that carbon has the plus charge, the carbon adjacent to where the electrophile added, and not the one that's sp3, right? You can't have an sp3 carbon and then have an additional plus charge. And then if you resonate that around, it is that carbon, and that carbon where we can move electrons and draw plus charge. So if, after this whole semester, You still have difficulty where those electrons go and how to draw resonance forms. You should practice. Okay, there are some aspects to this reaction which I want to highlight here. And in this Friedel-Crafts reaction, there are some problems with this reaction. Okay, one of the problems is the reactivity of benzene. So benzene itself, we can get to react with an electrophile. When we put a carbon group, an alkyl group, okay, alkyl groups are electron donating groups. We know that if you have more substituted carbons, you get more stable carbocations, right? So if you just think about a carbocation, if there are 3 alkyl groups on it, that's the most stable. That's because through those single bonds and through hyperconjugation, that's stabilizing the plus charge. Right? Remember that? Okay, so one of the aspects of the reactivity of benzene ring towards electrophiles, right? If we have an electrophile and then we have benzene, benzene is the nucleophile. So the more electron density you have, the more reactive it is. So what do you think would be more reactive towards an electrophile, benzene or methylbenzene? Methylbenzene. You put alkyl groups on and put electron donating groups on, what that's doing is making the ring more electron rich, making it a better nucleophile. So if you think about that, alkyl substituted benzene rings are more reactive than benzene. So what do you think the consequences of that would be if you tried to do this reaction? Well, you start with a pot of benzene, right? And then over time, you do this reaction, and then you start producing this product, and now you have a pot of benzene in this product. What do you think is going to react faster? The product will react faster. So one of the difficulties, I don't think your book really just talks about this, but it's an important aspect. If this is more reactive, what happens then is this gets alkylated faster than benzene itself, and so you have byproducts. You have a mixture of monoalkyl, and now there are 3 positions you could do it. I'll just say dialkyl. Okay, you start putting more than one group on. And that can cause some problems. So selective reactions sometimes is a problem. The other problem with doing a Friedel-Crafts alkylation is the fact that we have very reactive carbocations. So on the next slide, I have several examples of Friedel-Crafts alkylations, which shows you some of the difficulties. Not even talking about over-alkylating, putting more than one on. Let's just talk about the monoalkyl substitution. You can see here, if we do the reaction with benzene, and we carry out the reaction with tertiary butyl chloride, or 2-chloro-2-methylpropane, that works great. We get about 60% isolated yield of tertiary butyl benzene. Okay, no problem. That works really well. Methyl we can do. Nothing can happen with methyl. But if you take 1 butyl chloride, look at the second reaction. We do the reaction with 1 butyl chloride, we get 2 different products. We get about a 1-to-3 ratio, or 1-to-2 ratio, right? About a 1-to-2 ratio of, actually it's closer to 1-to-3. Normal butyl bromide and secondary butyl bromide. I'm sorry, secondary butyl benzene. What's happening? Well, obviously carbocations, if we form them, undergo rearrangements. They want to form the most stable carbocation. So certainly if your starting material is a primary chloride, that's not good. It'll rearrange to a secondary carbocation, and that's what adds to the benzene. And that's the major product, the rearranged alkyl group. Okay, and you see it's not a very clean reaction. We get a mixture. This one's look at this one. This one's very selective because what happens is you go from a primary chloride, which can rearrange now with a hydrogen transfer to a tertiary butyl carbocation. And that's the only thing that has, because this happens fast. As soon as you activate that chlorine and pull it off, you get the hydrogen shift, right, rearranging. So you actually do get a good selective reaction to form the tertiary butylbenzene. But let's say you didn't want that product. What if the product you really wanted was that one? Freeland-Crafts alkylation doesn't allow you to get that product because of that rearrangement. And in this case, if you wanted to form this product, well, this reaction might form a little bit of it, but it's certainly not very efficient, right? You're wasting a lot of materials making a different isomer. So how do we solve that? What we need to think about to do that for this second reaction and this third reaction, think about some kind of carbon electrophile that will give you the right carbon chain, but won't undergo rearrangement. Okay, so I don't know if we've never talked about anything like this, but what we can do instead of doing an alkyl halide is do an acyl halide. Another thing we could do to form carbocations, by the way, is our standard electrophilic addition to double bonds. So in this case, this is a nice symmetric cyclohexene. We don't have a problem with different carbocations here because it's all secondary carbocation. The difference here, instead of pulling off a chlorine or bromine to make a carbocation, we just protonate it with a strong acid like sulfuric acid. Now we have, let's say we protonate there, and then we form a carbocation. Now we have a carbocation electrophile, which can react. That's nothing new, right? We know many ways to make carbocations. Problem is, of course, if it has the ability to rearrange to a more stable one, it's not the product we get. Here's the problem that I just outlined. We want to make selectively the linear chain normal butyl, and we don't have a way to do that using Freeland-Crafts. We can do Freeland-Crafts acylation. So notice the difference. What I've done is change from an alkyl chloride starting material to what we call an acyl chloride. An acyl chloride, you'll learn a lot if you go on and take Chem 342, because they talk a lot about carboxylic acid derivatives. This is a derivative of carboxylic acids because it's a carbon with 3 bonds to other atoms, so 2 to oxygen, 1 to chlorine. It's a very electrophilic carbon, but even then not electrophilic enough to react with benzene. But what happens is that in the presence of aluminum trichloride, that can still pull off the chlorine with its electrons, leaving a plus charge behind. Okay, and notice the product. We have formed a carbon-carbon bond from the benzene to the acyl carbon. Okay, and there was no carbocation rearrangements. It didn't add to one of the other middle carbons. What's formed? What's the carbocation look like, and why is it stable or more stable than alkyl carbocation? Well, if you think about this process, the chlorine again has the possibility to donate electrons to the aluminum trichloride, and so in essence what happens is this comes off to form a carbon now that has bonds to oxygen, and I'll just write this as a plus charge. okay, plus aluminum tetrachloride. I'll draw it like this. With a formal minus charge on aluminum. Okay. What's so stable about that acyl carbocation?
Tertiary bonded carbon.
And no, it's not tertiary bonded carbon.
Okay, so oxygen splits off that. There you go.
Oxygen has lone pairs. Look what can happen. That lone pair, we can draw resonance form. That lone pair can stabilize that plus charge, so there's the 4 carbons. I'll just draw this. Let me just draw 3 bonds to the oxygen, okay? So the plus charge now is, there's 1 lone pair left, on the oxygen. I could draw that as a resonance form. So what's happening? Why is that more stable than a carbocation? So in this case, you would form just a primary alkyl carbocation, which would be rearranged to a secondary carbocation. But there's no way to spread out charge through resonance. In this case, what's happening is the plus charge on that carbon is being spread out to the oxygen through resonance. That's a more stable carbocation. That carbon is very electrophilic enough to react with the benzene electrons in the benzene pi system. So just like a very good electrophile, that's what happens. You can take that, and you could attack this carbon with a plus charge. Or if you're thinking about this resonance form, we could draw those electrons attacking and then pushing that back up onto the oxygen as a lone pair. Either way you think about it, that's the reaction that takes place. The nice thing is, because this is stabilized, you don't get any hydrogen migration or rearrangements. So those hydrogens will not rearrange. Okay, so this is called Friedel-Crafts acylation, not alkylation, because what we're doing is we're putting on an acyl group. Okay, well, that only gets us part way to solving our problem, right? We have been able to make a new carbon-carbon bond, which is great, and we've been able to do that without rearranging the carbon skeleton of the side chain. So instead of this versus this, we have the 4 carbons in a row. But we have something there that we don't necessarily need. Let's say we want this product. We have an extra oxygen. We need to get rid of it. Well, fortunately, there's a reaction. Here's a new reaction alert. When we have these acyl oxygens, these carbonyl oxygens, adjacent to a benzene ring, remember that benzylic position is more prone to reactivity. We can reduce that. And there are 2 ways to do that. Either zinc under acidic conditions, and this is actually a zinc-mercury amalgam. It tends to allow electron transfer easier. So your book draws this as zinc-mercury. It's an amalgam of those 2 metals in the presence of HCl or other strong acid. That goes through electron transfer to the CO bond. Eventually you take off the oxygen completely, and you make alkane. I'm not going to worry about the mechanisms for these. They're a little bit more complicated. This one especially, by the way, if you are interested, this is called a Wolff-Kishner reduction, named after the people who studied it. It's hydrazine. You end up making N2 and then reducing this to the alkane. And water is the other byproduct. But the nice thing is we have methods to convert that to an alkane, which is good because now what we have essentially is instead of doing this in 1 step and getting a mixture of things, we can actually just do 2 steps where we can control the carbon skeleton from rearranging and then take away the oxygen and get to our product. Okay, that's the only way you really can do that without the rearrangement problems. Okay, another aspect is that makes acylation better and again, your book doesn't really describe this too much, but this is, when I talk about the fact that alkyl benzenes are more reactive than benzene itself, because those groups are electron donating. Well, what do you think is the nature of this acyl group? Is it going to be electron donating or electron withdrawing? I heard someone say electron withdrawing. That's right. If you think about that CO double bond, you can write a resonance form for that. I'm just going to draw the CO bond part. Where you put those electrons up on the oxygen, okay, like that. What that indicates to you is that a carbonyl group, the carbon of a carbonyl group is electron deficient, and so this is an electron withdrawing group. What do you think that will do to the reactivity of the benzene ring it's attached to? If you're removing some of that electron density from the benzene ring or lowering its energy, it's going to be less reactive. So guess what? Not only does Friedel-Crafts acylation allow us to control how avoid rearrangements of the carbon skeleton, it's also less reactive than benzene. So we also avoid the problem of overreaction. So we have two things in our favor for this. So practically, if you want to do carbon substitution of benzene rings, Friedel-Crafts acylation is the better way to do that. Okay? Okay, well, that leads up to this aspect. So here I've shown 4 benzene derivatives, and I've shown their relative reactivity. Okay, benzene having a relative reactivity of 1. So if you think about any, just bromination or nitration or something, you look at benzene, okay, and it reacts at a reaction rate arbitrarily of 1. All right. If we have on there, instead of benzene, we use hydroxybenzene or phenol as the starting material, and then do bromination or nitration or some electrophilic addition, a substitution, it reacts 1,000 times faster. Okay? On the other hand, chlorobenzene reacts slower than benzene, and notice nitrobenzene reacts a whole lot slower than benzene. Really unreactive, 0.00000006, something like that, times as fast. 10 to the minus 8 relative rate. Okay, so what's the difference between these substituents?
All the electron withdrawing from
Yeah, and that's what's a little bit confusing about this. So he's absolutely right that the oxygen is more electronegative atom, and so the oxygen you might think as being an electron withdrawing group, right? But in fact, oxygen, what oxygen is very good at is donating its lone pair. So if you think about phenol, let's say I take one of the lone pairs of oxygen down and then push the electrons up here. Let's just draw some resonance forms. Okay. I could draw the resonance form. Notice what happens. Electron density went into the ring. We have a negative, if I draw this resonance form, negative charge in the ring. Okay? And I could spread that out. I could draw it down here, push that up here. I could draw another resonance form. Like this. Okay? With a plus and minus. And then I could draw another resonance form. So those 3 carbon positions all have negative charges. Draw it there. All right? So what is oxygen doing? It's not just the single bond. And yes, you're right that that single bond might be polarized towards the oxygen. But the fact that oxygen can share its lone pair and donate it into the ring actually makes the ring more electron rich. And it's the resonance effects that contribute to the reactivity, the ability of oxygen to donate electron density. So if you can imagine, now I've just drawn this with the neutral phenol. If I were to react an electrophile to this and generate a carbocation in there, that oxygen could stabilize it, right? So that's actually, in terms of this, the pi bond in the pi system, that lone pair is donating towards the pi system of the ring. Okay, so it's actually a very strong electron donating group, which may not be apparent or might not have been apparent up front because of resonance. Okay, and resonance is a very strong stabilizing factor. Just remember that. The chlorine, yeah, chlorine is more electronegative than oxygen. So what happens here is it's a little bit less reactive than benzene, and it is the electron withdrawing nature of it that contributes to a little bit less reactive. Nitro group, as I said, if you remember the Lewis structure for nitro group, okay, because there's a full formal plus charge on the nitrogen, it's always going to be a very strong electron withdrawing group. Okay, so it's no surprise, nitro is one of the strongest deactivating groups for benzene rings. We refer to this as an activating group and nitro as a deactivating group. Relative to benzene, with no substituent or with hydrogen. Okay. Now there are a number of donating groups and electron withdrawing groups we can talk about. Things like, let's just say if I have a CH3 attached to the benzene ring. Okay, I already talked about that as being it's an electron donating group. But it's only electron donating group really through hyperconjugation or through sigma bond inductively. Okay? It's not a resonance electron donating group like oxygen. So relative to an OH group, this is a weaker, much weaker electron donating group. So the effect will be less. I don't know exactly how it fits on the scale relative to benzene. It'll be a little bit more reactive than benzene. Something like a CF3 group. How do you think that would behave? What have I done? I've changed from CH3 now to CF3. And there's no lone pairs or anything to be involved in resonance. So again, it's just inductive effect. But this is an electron withdrawing group. Why? Well, if you think about CF3, it has 3 very electronegative fluorines on it, each withdrawing electron density inductively, which makes the positive charge on the carbon. So like CF3, a withdrawing group, where CH3 is a donating group. So you see how that all balances? So here are some more. Activating groups, as I said, alkyl. These are electron donating groups. Alkyl, oxygen base, so directly attached to oxygen, again, because of the presence of a lone pair. Nitrogen also has a lone pair, so nitrogen is a pretty good activating electron donating group. And even sulfur. Sulfur has lone pairs like oxygen. That can help activate a ring. Alkyl, a weak electron donating group because there's no resonance contribution, but these with lone pairs are stronger because they have resonance contribution. Okay, so all of those make the benzene ring more reactive if they're on there. Groups which withdraw electron density, here are some more of them. As I talked about, an acyl group, because that's electron withdrawing. The sulfonic acid group is electron withdrawing. Nitro group is very electron withdrawing, one of the strongest. A cyano group, okay, again, because of the polarity of that pi bond. The cyano group is electron withdrawing, deactivating. Halogens, Fluorine, chlorine, bromine. Those are all pretty strong electron withdrawing groups inductively, but much weaker, I think, than a full-blown NO2 or something. So this is sort of a, I would say, nitro is probably one of the strongest. So those sort of give you a divide, and you have to think about when you're doing reactions on benzenes that already have a group on it, you really need to think about how that substituent affects the reactivity. Okay? And there's more to it than that as well. If you think about this particular substituted benzenes, okay, we have benzene with 6 hydrogens on it, okay. All positions are equivalent. Once you start to put another group on, OH, Cl, NO2, alkyl, acyl, sulfonic acid, whatever, once you already have one group on it, and then you do another reaction, let's say we do bromination, okay, where does the bromine go? Now the positions are no longer equivalent. There are several possible products, actually 3 possible products. The ortho, remember ortho, meta, para? 1, 3 is ortho, meta, and para. Okay, so we have 3 possible isomers, regioisomers. They're constitutional isomers because the bromine's in a different position relative to the other group. What controls that? Those are questions you should ask. Is it selective? What controls it? And how can we think about that influencing other reactions? So I think I have some data on the next slide here. Yes. Here is the nitration. The nitration of methylbenzene. Methyl, as I just said, is a weakly electron donating group. Okay. It activates the reactivity of the benzene ring. If you substitute one of the hydrogens on the benzene ring for a NO2 group under our conditions of nitric and sulfuric acid, we see 3 products. But they're not all formed in the same amount. Okay. We see ortho product, and the para product predominating. Even then, not the same amount, 63 and 34. But notice this meta product, only a little trace of that's formed. Okay, only a little trace. So why do you think there would be a difference between, say, ortho, adding the nitro group to the ortho position, or to the meta position? Why would we get more of one and not the other? I hope throughout this semester you've learned that the major pathway in a reaction is the one which is the lowest energy path. Okay? So what this says is that by adding our electrophile to the ortho or para position, that's more favorable. It must be a lower energy path than adding an electrophile to the meta position when we have a CH3 on there. So let's take a look at that. With the mechanism we know, okay, let's take NO2 plus and add it to the ortho position. So if I take this bond here and react it with NO2 plus, which is what's generated, mixing those together, we form the sp3 tetrahedral intermediate, okay, with the plus charge then on the adjacent carbon. So notice, I add the nitro group at the meta carbon, I'm sorry, at the ortho carbon, but the plus charge is in the meta position. Okay, that's initially formed when I break that bond. Okay, now look at the three positions where that plus charge is if we draw the resonance forms. Okay. It alternates now to here. Okay. So what I did was I shifted these electrons over, leaving the carbon there empty. All right. And then I can draw one more. I can shift these down, leaving the final carbon empty. That's this one. Okay. So if you add the group in the ortho position, you generate an intermediate where we can draw that plus charge in those three positions, right? What happens if we add instead that nitro group added to the meta position? We draw that. In that case, relative to the CH3 that was already on there, I'll put the plus charge here. And the nitro group there. Okay? Where are the three positions that the plus charge ends up? But if we draw the three resonance forms. We can move this over here. That leaves this carbon empty. Okay? Or we can move this up here. And the third resonance form puts the plus charge on the bottom carbon. Okay? So those are the two possible intermediates that could be generated if we add ortho or we add meta. By the way, if I add the group para, I'm not going to draw it out here. If I add the group para, I also get plus charge in those three positions. Okay, the same as the ortho. So what do you think? Which of those carbocation intermediates is more stable? And why?
The one above the meter is more stable because it stabilized by the two double bonds.
All of them, well, what I mean is this set of resonance forms or this set of resonance forms. Which is more stable? The one on the top. And that's more stable because notice, CH3 is an electron donating group. Electron donating. So if the plus charge is directly adjacent to the electron donating group in one of the resonance forms that you draw, none of these resonance forms on the bottom does that situation take place, right? Here we have, if you will, think about it, a secondary carbocation, a secondary carbocation, and a secondary carbocation on the bottom. In the top, we have a secondary carbocation, a secondary carbocation, and a tertiary carbocation. So overall, which is going to be lower in energy? The one with the more stabilized carbocation as one of the resonance forms. So these are two competing pathways on the energy diagram. This one is the lower energy pathway. That's why we get more of it. Okay. The para also will place one of the plus charges next to the electron donating group. Makes sense, right? Okay, what about if instead of CH3, which is electron donating, I have an electron withdrawing group? What would you predict as the major product? Here's the example with CF3. Remember I said CF3 was an electron withdrawing group? Because of all those electronegative fluorines. Guess what? Look at the major product. It's meta. To an overwhelming amount. Why? Because if you add the nitro group in the ortho position or the para position, either one, and you should draw out those resonance forms to convince yourself. I'll just show the para position. Okay, one of the, if we add there, one of the intermediate carbocations will place it in that position. Okay. We just saw in the previous slide, ortho would put one of the resonance forms with a plus charge next to the other substituent. That was there originally. Now, since we have an electron withdrawing group, and we want to put a plus charge next to an electron withdrawing group would be a worse situation. It'd be a higher energy situation. What we want to lower energy would be to donate to it. Okay? So if we're withdrawing even more plus charge, we're raising the energy of the carbocation. So in this case, if we add ortho or para, one of the intermediates is a higher energy carbocation. If we add to meta, we avoid that. None of them are particularly stabilized by any donate groups, but none of them are particularly destabilized by putting it right next to a withdrawing group. Okay, so the nature of the group, if you're doing to make a di-substituted benzene, you have something on there already. The electronic nature of that substituent is critically important. I think I have some of these actually drawn out for you. So here's the example of phenol, generically phenol, and activating groups. So in general, groups that are activating are electron donating, and if they are resonance donating, they have even stronger effects. So here are all of the possibilities for phenol. Adding an electrophile, I didn't draw the product losing the hydrogen yet, but the intermediates are what's formed. So if I add ortho, I get a plus charge adjacent. You draw the resonance forms, that puts the plus charge here, here, and now here. Okay? You put the plus charge next to the oxygen, then you can spread it out even further. Actually, if you have resonance donating abilities, lone pair donating abilities, you can draw a fourth resonance form, putting that group on there. Okay? Notice if I add to the para position down here, I also form resonance forms where the carbocation is in 3 positions on the ring. Again, one of them is right next to the donating group, and we can draw a similar stabilized carbocation from there. So those two, ortho, para, either one, have an especially stabilized, one of the resonance forms is especially stable, whereas meta, they're all, again, the secondary carbocation, none of them are being lowered in energy. None are raised in energy, but none are lowered in energy. Here, intermediate is lowered in energy. So groups that do that, as I said, alkyl, oxygen, nitrogen, sulfur, anything that has a good lone pair on it that can donate well as a lone pair can stabilize that intermediate. Okay? Electron withdrawing groups, I have the exact same resonance forms now with a nitro group. And again, since we have now a strong electron withdrawing group, it favors the meta addition because that's the only one that avoids particularly bad situations. Putting the carbocation right next to the electron withdrawing group raises the energy, it destabilizes, and it's a higher energy path. Okay? So notice nitro, sulfonic acid, acyl, cyano, and many, many other groups. You just have to think about the structure and the electronic nature. Okay? We're going to talk more about this and then talk about some ways we can use this to design selective additions of multiple groups on Friday.